Welcome to SICE Petro's presentation today. We are going to cover examples of how to use iMineralysis multi-well models CSV summaries. And we're going to use those for data analytics and model QC. I'm Mike Uland. So things we're going to look at is that in addition to exporting your modeled logs as LAS files, fluids, lithology, iMineralysis can also output these flat files, CSV, separated variables, parameters, and that includes log error estimates, the final optimized matrix coefficients for the inversion, and the averages for the modeled lithologies and fluids by zone. And they can be imported to Excel directly, they're CSV files, or most data analytics programs or geomodels will also read the CSV files. I use them to help me understand what's going on when I have to deal with dozens to hundreds of wells with multiple vertical zones and the geology and the fluids that may be changing both aerially and vertically. Helps me sort out what are the changes due to geology and fluids, or are they simply a trend of higher model error? We're going to look at three examples. First example, I'm going to take one of the CSVs from one of the projects, data summaries from iMineralysis, and we'll take that into a 2D mapping program. In this case, IHS is Petra. And I'm just going to do some quick look plots and maps. Just standard stuff that you'd do with your 2D mapping program. We're going to load the exact same data set to data analytics programs. That could be Spotfire. In this case, it's going to be SAS Jump, so that we can do some interactive QC with the plots. And last example, we're going to load it to Python. And we're going to do a little tiny bit of custom QC and uncertainty. What do these things look like? They're just a flat file. They're an ASCII file, a comma-separated variable. Same thing you'd use with Excel. And in fact, Excel imports them directly. And you can make your plots right from Excel. You can also put them in Spotfire, in this case, Jump. We're going to look at some Python, but it works with R and MATLAB. And you can take it to packages like Geographics or Petra. We're going to use Petra today. And pick your favorite 3D model. You could use it for quality control inside Petrel or GoCAD. Pick your favorite one. First example. So we're going to load the CSV to a 2D mapping package. We're going to do a little checking in map view and crossplot. Okay, so I've loaded the data, and there's 4 plots here. Now, all of the plots on the x-axis have the average model error. So that's the reconstructed curves versus the original curves. What is the error and overall input curves? Gamma ray, DT, rho B, etc. So total model error on the x-axis. And we're going to look at some of the zone averages for quartz or bulk volume gas, shale, average calcite. And they're color-coded in this case for the reconstructed error of just the PEF curve. So things we see in quartz, as I get less quartz, I get higher PEF error. If I get less bulk volume gas, and I wouldn't really say that's a very good correlation, pretty much a straight line. In the case of shale, the more shale I have, the higher the PEF reconstructed error. And we're going to see later, if we look at this closely in some of the data analytics programs, that because this is primarily a clastic reservoir, the more shale you have, the less quartz you're going to have, and the PE has trouble in the shales, not the quartz. So we're going to look at some map views, and all we did is take those average shale calcite quartz and porosity volumes, basically add up to 1, and we're going to show that as a pie diagram in map view. We got more clastics and we got less clastics on the left, but I circled 2 of the wells. I was a little suspicious. That well looks okay. It looks like it's offsets, but that well doesn't. So maybe there's a problem here. So let's go look at the average errors. Okay, so what we have here is the average error for each of the reconstructed curves. PEF being in orange, gamma ray being in green, conductivity being in cyan. Everything adds up, total errors. Some of these bubbles would be a little bigger, some of these bubbles would be a little bit less. I've normalized them. But if we look closely, this well looks a lot like its offsets in terms of error. It's this one that stands out. We're going to go back one slide. Maybe we won't go back one slide. But if you look at those errors, they don't affect the fluids, and PE shouldn't in the fluids. So we're kind of happy with that. Let's look at example number 2. Here we're going to load exactly the same CSV file, and we're going to put it into a data analytics program. Could be Spotfire, could be your favorite program. In this case, we're going to use Jump. So what happens here is you pick out your CSV file, drop and drag it into the input window, and it immediately decodes the headers for you and the data columns for the different wells. In this case, 27 wells, I think, is what I put in here. And it decodes those in a menu. And then from that menu, I can pull out a graph or analytics. I'm going to pull out a graph here. I'm going to select a graph. I selected a scatter plot. And I'm going to highlight some, in this case, some of the average variables we looked at before, including the average error. Drop and drag those into the data window, and we're ready to go. So this is what this looked like. It was a scatter plot, and it was by service company and by well. And it's the average mineralogy and average fluids. What did that look like by service company or by well? And I didn't see any real super big trends in there that I got excited about. So the next thing I did is I made a ternary diagram of the major lithologies. And one of the things you can do, and I do like about whether it's Spotfire or any of the other interactive analytics programs, is that you can highlight data points in any graph and then link those to other graphs. So the points that I selected that in the red area, they immediately show up, and I can subset those to other graphs or export that, or the blue area. And then they immediately show back up in my scatter plot and others. So that's pretty nice. One of the other things I did is I looked at all 27 wells down the vertical axis against their errors, individual errors in the curve reconstructions. So you can see if it's blue all the way across, that well might not be right, but at least it can perfectly reconstruct all the input curves. But there are wells where it doesn't, in red, it doesn't reconstruct all the input curves. And more interesting is it's not always the same curve in the same well. Different things are going on here. That might be a data quality curve input problem. Might be. All right, we'll look at our last example. Same CSV file. This time I'm going to take it to Python. You could take it to MATLAB, you could take it to R. I'll pick your favorite one. But we're going to look at this data a little closer. The same kind of thing, exactly the same flat file or CSV ASCII file, except now we're going to use Python and we're going to import it as a Panda. And we're going to take a look at what the lists of the data are and the data types, and we're going to set up to start iterating through plots. And the nice thing about some of these programs, whether it's MATLAB or Spotfire, once you have the script set up, you can begin to slice through data a little faster. So in this case, we're going to have two plots on the left. Map view, and I'm looking color-coded for water saturated SW. And the same map view on the lower left for volume of shale. And one of the things I was looking at when you start looking at a map view is a really high water saturation well next to a lower water saturation. High against a low. Is that possible? Maybe it's just the shale. Okay, well that would make some sense, but it doesn't make any sense here. So we're going to take both of these variables, SW and shale, and we're going to cross plot them against themselves. So SW against V shale, and all the best gas is at low V shale and good water saturations, and that's exactly where it should be. So this probably isn't a problem. You just have a good well against a bad well and a better well against a bad well. And you'd go check that with production, and we did. Straight Buckles plot or bulk volume water plot. So you're going to plot the same SW and now against porosity. And you would expect your best gas volumes when you color code for bulk volume gas. You'd expect that to be in the lower quadrant. And it is. So everything's looking pretty good. Let's go look a little closer. It's a busy slide. So if you remember from previous iMineralysis presentations or just any type of petrophysical inversion, you're solving for lithology and fluids, and you're going to reconstruct the original red input curves with the blue modeled curves. And in this case, I'm going to take the difference, or iMineralysis does this for you, and it puts that in the CSV summary file for you. All I've done is load that for these plots in Python. And what you're really doing is looking at that error on the reconstructed. And in this case, it's a total error. It's across all curves. And I'm going to bring in that average reconstructed error in a scatter plot against the average of the fluids and the minerals. And each dot is a well. So each dot represents one of these wells. And things that begin to stand out, there's some are just scattered, but there are other things like quartz versus V shale that are very linear. And that's to be expected. It's a linear model. So as the quartz percentage goes down, the V shale increases, and we saw that on some of the other plots. Not that big a deal. But if I start looking at this average error, that begins to be more interesting. There's some interesting trends there. So we'll go look at that quartz. And as the average quartz increased, the average error went down. So the problem is with the shale. Not just on the PEF curve, but the shale has given the model a little bit of trouble. That's probably because we're solving for one shale rather than shale minerals. Still a pretty good match. All right, so we're going to look at this a little closer again. Now remember that when we get done with hundreds or thousands of genetically optimized runs and we get a final optimized coefficient that we're going to use for our minerals, fluids, and our input logs, we're going to output into this CSV file what those final coefficients are that gave us our best match for each set of curves. And in this case, instead of doing the totals like I did before against total lithologies or total error, I'm going to pick out just the neutron. And you can pick out any of these. I'm going to pick out just the neutron. and I'm going to look at its final coefficients for fluids and minerals, and I'm going to look at that against the Nphi reconstructed curve error. So not the total model, just the red-blue error where it didn't match up. So places like this, where it didn't match up. I'm going to plot just that mismatch. And there's some other interesting things, a lot of data scatter going on here. But one of the things that I noticed here is that, for shale, we come across, and we're going to look at the Nphi shale coefficient versus the calcite. And in general, it's pretty flat. It's pretty uniform. Gets about the same answer. We get 3 or 4 data points that are way, 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 way different. And I am suspicious of that. So did the Nphi coefficient for shale go from around 20% to 30% for just a couple of wells? I'm not so sure about that. I don't think the geology is changing that fast in this area. So these would be 3 or 4 points that I would go back and look at pretty closely on the model and see where the problem might be. All right. So all stuff that you know before you start any of these inversions, pay attention to, just like that last slide, pay attention to your input data, or if you've missed it, go back. If you highlighted in the data analytics that those are outliers, go back and take a look at, are we just in a bad hole interval and we didn't get it flagged correctly? The standard QC work, we showed earlier on in that first example, just look at some cross plots and map views and always check it against your core data if you have it, or XRD. And what we looked at today is these CSV model summaries coming out of the inversion models for each well and each zone. And you can take that right into data analytics programs. And you can look to see that wells look okay in cross-section, but maybe they have higher model error like I was looking at before. Then you start looking at that closer. Maybe that's just poor input logs, or I didn't get the bad hole flag set correctly. Or maybe I've missed some assumptions in the model for how that shale is varying across that area. I look at it to investigate those reconstructed curves also. If nothing else, remember that all petrophysics models are wrong. I use them all the time, but they're wrong. Keep that in mind. But they're very useful. And if you calibrate them, the plausible models are very useful for constraining your geomodels and flowsim models. So, for more information, if you're interested, contact Petra, or you can follow us at LinkedIn. And special thanks to Rinaldo and Kevin and Patricia, who basically made this all possible. Okay, thanks a lot.